Okay, so let me welcome everyone in our afternoon session for today. So the program will be similar to previous days. So we will have two talks, and then we have again a space for gather, and then at 7 of Central European time at least, we will have a poster session. So instead of gong show talks, we will have posters, which will take place in gather. And you can see in the email that you got, there is a map where you can find the poster session. It's in the northeast of the entrance of the main hall, let's say. And the authors of the posters are encouraged to be there so that they can stand next to their poster and people can come and ask them questions. And there will be some organizers around in case something goes wrong. Okay. So for now, let's welcome our first speaker, which is Alex Arvanitakis, and he will be talking about the BFV perspective on brane currents. So Alex, the floor is yours.
Thank you very much. Thanks for the invitation. Hi from Greece. It's a pleasure to participate in this conference. And I'm going to talk to you about my lockdown paper, which I wrote mostly last year, appeared a few months ago this year. So what is this about? So put briefly, it's a construction of a Poisson algebra, which describes the phase space of a brane in general, brane meaning strings or higher branes as in string or M theory, given the data of a graded symplectic manifold with a vector field that squares to 0, or a QP manifold. Or these are also called symplectic L-infinity algebroids. Some of you might like that name better. And physically, that data is encodes the fluxes and the gauge transformations of the supergravity theory that describes the background where the brane is propagating. Okay, and the tools to be used in this construction are the AKZ construction of topological field theories from the same QP manifold data, plus this not really novel but extremely obscure apparently ingredient, which is the zero locus reduction of graded Poisson algebras due to these lovely people, which has not been used by anyone else to my knowledge. So I think this deserves to be better known. Okay, so this construction gives a general picture where for every P brane, you have a QP manifold of, these are classified by the degree, which is the degree of the symplectic form. I will explain that shortly. Or if you want, in general, these are not like infinitely horrible L-infinity algebroids. These are L something, where something is P minus 1, if I remember correctly. But, you know, these are naming conventions, so I didn't dare put a number to it. So some of this was known since the late 90s, I guess. So, for example, courant algebroids, which are degree 2 QP manifolds, correspond to strings. So that's the first entry in the table here. But then the rest of the entries were really put forward. This correspondence was really sketched quite recently. And what's really novel and what happened very recently is that the QP manifolds for branes with world volume gauge fields, such as the D3 brane or the M5 brane, and various other D branes, which we will write up eventually, the corresponding QP manifolds were also written down very recently. Whereas for the fundamental string and the M2 brane, there are no world volume gauge fields, so the QP manifold was known, but you didn't have enough examples to notice the pattern. But it was only once these objects were constructed that the pattern was made clear. Okay, so for all of these stringy examples, you have a source Q manifold, a graded supermanifold, which is just a shifted tangent bundle for some compact real orientable sigma. And you get a real Poisson algebra. But like in the AKZ formalism, you can trade that source Q manifold for anything that has a Q structure and a homological vector, a Q structure and an integral. So for example, you can have a Calabi-Yau and you can form an anti-holomorphic shifted tangent bundle. And you can get holomorphic analogs of everything I'm going to talk about shortly. So this is very nice. Physically, what this does for us is it explains the various disparate observations in the literature where you calculated Poisson brackets of brane currents, and then you found nice geometric expressions in terms of target space geometry, in fact, generalized geometry. For strings, you get Hitchin-Gualtieri, classical generalized geometry, whereas for higher branes, you get what's known as exceptional generalized geometry. Exceptional is not a special case, it's a generalization. It's to do with the relationship between the exceptional Lie groups and supergravity. So let's get right to it. So some of the story, as I said, was known for, especially for strings, since the 90s. Well, and I'm going to outline some of the relation between generalized geometry and string currents, which was understood already in 2005 by Alexiev and Strobel. So you take your Nabu-Goto string and then you introduce momenta. All of this is in phase space. So instead of having second order equations of motion in position space, you add momenta and then you have first order in time equations of motion. And then you get an action like this. We're only going to care about the first term here, which basically is the symplectic structure of the phase space. And this first term then gives rise to the standard Poisson brackets that you might have seen if you've looked at brane physics. So positions and momenta both depend on the coordinate sigma of the point in the circle, and then you get a Dirac delta function on the right-hand side. Now, the point is, because the momenta are naturally one forms on S1, it's good to organize the functions on phase space in terms of degree, in terms of differential form degree. So if you organize them, and because S1 is one-dimensional, you get just one forms and you get zero forms. So if you look at the one forms, you get every such current corresponds to a section of T plus T star, where V is the vector and lambda is a one form. And at zero forms, you just get things that correspond to functions on the target space M, where M is the space where the string is propagating. And in fact, this is a feature which will persist when we discuss higher branes, when I outline how higher branes work. Okay, so here's what these people did. They took the Poisson bracket of these one form things, and then they just directly calculated the current algebra. It's not very complicated. You can do it by the time I finish talking about this slide. And it's a very simple calculation, but what's non-trivial about it is that the right-hand side is closed in terms of the types of currents we just discussed. So here, in the first term on the right-hand side, we get a one-form current, but for LVU, which is another section of T plus T star, which is the generalized Lie derivative of generalized geometry. And then the other term, which is called the Schwinger term by some physicists, you get the ODD structure, again in ODD generalized geometry. So the natural ODD metric is the one that pairs V with kappa and lambda with u. Okay, that should be obvious from the notation. So the key to generalizing this to any other brane you might like is to exploit the insight which actually predates generalized geometry of Reutenberg in 1999, that both operations are built from the Q structure and the graded symplectic form on a QP manifold, which is what I'm going to explain in the rest of this talk. Okay, so what are these QP manifold objects? These came up already, certainly today in the AKZ talk earlier, probably the days before as well, but I might as well summarize. You take a super manifold and you take a vector field which is odd and is nilpotent, q squared equals 0. And you also take a symplectic form, and all of these things need to be compatible with each other. And crucially, the supermanifold is graded, so every coordinate has a degree. In our case, it's an integer that's greater than 0, and it determines the Grassmann parity. So odd coordinates anti-commute and even coordinates commute. Okay. Q is a derivation of the ring of functions on the supermanifold of degree +1. You get minus signs when you move it past objects, as usual. And crucially, the symplectic form also is homogeneous in degree. Well, you can have any degree greater than or equal to 0, big P. And essentially what this means is if you write it in Darboux coordinates, then you get omega equals dp dq, and then the degree of P and the degree of Q, just the sum is equal to big P. Okay, so this is this big P kind of determines how up to homotopy the QP manifold is, viewed as a symplectic L infinity algebroid. The higher the P is, the more homotopies you have to deal with. But I'm not going to be taking this point of view. And for those of you who are familiar with the BV or antifield formalism, I should note that you can, it's not a special case of what I just talked about, because you have negative degree coordinates that change your lifestyle completely. But if you disregard that, then it's a special case of this, where big P equals to -1. Okay. Now, a good way to think about these QP manifolds is that they are machines that house lots of vector bundles and operations between them. And you get the vector bundles by counting the degrees of functions on the, well, in the ring of functions over the supermanifold. And because all of the coordinate degrees are non-negative, you get some finite sequence of vector bundles corresponding to functions on the supermanifold at fixed degree. Okay. In fact, secretly, we're all familiar with how this works, because differential forms form a Q manifold. It doesn't have a symplectic structure. So how do you view a differential form as a function supermanifold? Well, you write it out in coordinates, and then you convert the coordinate differentials dx to fermions c. And then you say, well, I have the original coordinates on the underlying ordinary manifold have degree 0, and the new coordinates have degree 1. And then the Q structure is the de Rham differential. And we see that the space of functions at fixed degree n is just the differential forms of rank n in this case. This example is kind of the motivating example for most of what I'll be talking about. And this one in particular is especially nice because it has a supersymmetric Berzin integral, which is just the integral of differential forms. If it's a top form, you integrate it. If it's anything other than a top form, you set it to 0. Okay, it's very straightforward. So it reduces degree by minus the dimension of m. And I'm assuming that everything is connected, of course. Okay, so let's look at an example. So this is the example of the QP manifold that will eventually be responsible for the Alexeyev-Strobel current algebra I showed a few slides ago. So you take T1M, the shifted tangent bundle, and then you take the cotangent bundle with a degree shift, and this amounts to this ring of functions. You have x mu are coordinates on the original manifold, unadorned M, and then you have psi's, which are coordinate differentials, and then you have their conjugate momenta. So the symplectic form that this object has takes the form I displayed a few slides ago. So P is the conjugate momentum to X and it has degree 2, and chi is the conjugate momentum to Psi and it has degree 1. So that omega is a degree P, big P equals to symplectic form. And let's say we pick the Q structure where Qx equals psi, Q psi equals 0, etc. Clearly, this squares to 0 and is good. And I'm telling you that it's also compatible with the symplectic structure with this choice of signs. So in this case, the ring of functions of degree 1 on this curly M is T plus T star, which is the same bundle we are familiar with from generalized geometry. And in degree 0, we just get functions over the body. And you can calculate, this is a quick and easy calculation again, that the ODD structure, V bullet U, is just the Poisson bracket of degree 1 things. And the generalized Lie derivative is this derived bracket expression. You hit V with Q and then you take the Poisson bracket. Okay, so the point is, if you've expressed everything in terms of the Poisson structure, and the Poisson and the Q structure, this is what will generalize to any QP manifold you might want. Okay, so we have one QP manifold. How do we get what looks like a brane phase space from this? There's two steps. Firstly, you form the space of maps from the shifted tangent bundle of the world volume to the target space QP manifold. And the AKZ construction tells us that if this source manifold over here has an integral, for example, if sigma is compact, it has an integral. The space of maps is a QP manifold, but the symplectic form undergoes a shift because every time you do an integral, you subtract the dimensionality of sigma. Is the reason why you get a shift. So you get, so the space of maps is a QP manifold of degree p minus dimensionality of sigma. But that gives you too many superfields. You can already see this from here. You have 1, 2, 3, 4 things, but the string positions and momenta are just 2 things, have entirely too many. So what helps you is that, so what you need to do next is that you perform this obscure operation invented by the Russians, the zero locus reduction, to arrive at the correct phase space. And this gives you the phase space as a Poisson algebra in general, in complete generality. And in favorable examples, this is obviously the Poisson algebra arising from some infinite dimensional manifold of mappings. Okay, so how does this zero locus reduction work? Say you take your graded Poisson algebra with, I'm going to denote it with the square brackets, and big P is the space where the vector space where the Poisson algebra lives. The algebra, the underlying algebra, sorry. And say the Poisson structure has degree minus n. So if it's symplectic, it comes from a symplectic form with degree plus n. And you pick some z, which is a vector field, and which is of degree plus 1 squares to 0. And then you form this derived bracket expression. So for any f comma g in the Poisson algebra, you take the bracket of f with z hitting g. And you take the quotient where basically you set anything that's z exact to 0. Okay, so you quotient by the ideal generated by the vector field z. Now, if you count the degrees, you find that the new bracket, if it is a Poisson bracket, must have degree shifted with respect to the original one by 1. And that's it. So this serial locus quotient makes this expression be a Poisson bracket. You can check that. In fact, I checked it very explicitly in the paper. And yes, that's all there is to it, isn't there? So we take our construction. So we take the graded Poisson algebra arising from the space of maps from the shifted tangent bundle of the world volume, in fact, the world space, to the QP manifold. And then we have AKZ tells us there is a good Z that squares to 0. And it's built out of 2 objects. You get the de Round differential on the source manifold, and then you get the Q structure on the target space QP manifold. And the 2 things are going to commute because they were lifted to the space of maps. In fact, they're going to anti-commute because they're both odd. And because we want to find the space, because we want the brane phase space to be as a Poisson algebra of degree 0, we want the new bracket to be of degree 0. And this eventually fixes the dimensionality of the world volume in relation to the degree of the target space symplectic structure. And this is different from the usual AKZ type story, where if you had an AKZ type setup, you want the dimensionality of sigma to be p plus 1, so that the Hamiltonian of this vector field Z is degree 0, and the square bracket has degree plus 1, which is the usual BV choice. So that's not what we're doing. We're using this anti-anti bracket, which is the degree minus 1. Of course, you could view this as a BV bracket if you flip the degrees around, but that's not what people usually do when they discuss the BV structure arising from the AKZ setup. So the dimensionality is such that physically, sigma corresponds to a space-like section of the associated P brane. So actually, the dimensionality of the world volume is P plus 1, and sigma is just the world volume space. And this is what we naturally expect, because when you write down the brane Hamiltonian formalisms, you split time and space apart, and so you're really dealing with time evolution on spatial brane configurations. Whereas for AKZ, indeed, the dimensionality of the world volume is P plus 1. Big P plus 1, in fact. Okay, so how does this apply to our toy example? Return to the previous setup, which is the P equals to QP manifold, with the very easy Q structure over here. And then we form the space of maps from the shifted tangent bundle of the circle to this target space. And we need to have the circle because it works out the dimensionality of the source manifold sigma needs to be 1. So if it's compact and connected, it's a circle. So we get 4 superfields for every coordinate on the target. Sorry, we get 4 kinds of superfields. And they depend on the coordinate of the circle and d sigma, which is the differential, which corresponds to the odd coordinate on T1, S1. And then when you expand these superfields and you get component fields, these are naturally differential forms on sigma, and they have various degree assignments, which I'm not going to go into. And then we clearly have too many superfields and component fields going around. So what's the ZL reduction? So we set basically this Q on the superfields equal to the Durand differential on T1S1. And because Q has this simple form, it amounts to fixing C in terms of the X superfield and fixing P in terms of the chi superfield. So we get, once we do the reduction, we end up with 2 kinds of superfields instead of 4. We get these X superfields and we get these chi superfields. And it turns out this is the correct object. So the degree 0 bit of X is a differential form of rank 0 on the S1, which is the string position. And the degree 0 thing in chi is the rank 1 form on the S1, which is the string momentum. You also get some ghost things, which I don't care to comment on at the moment, but they're perfectly nice. They sort of, if you include the ghosts, this is naturally the phase space of a spinning string, if you want. Okay, so how does this work in terms of, how does this work in general? Say you have some arbitrary target QP manifold. Then you have a nice definition of currents, which I'm going to define smeared against test forms, differential forms on sigma, because I don't necessarily want to deal with Dirac delta functions in the current algebra. It's bad for your health. Okay, so you take the function, you write in terms of superfields, you hit it with a test form on the source, and then you integrate over the source. And you then just go into the definition of the new Poisson structure obtained via the 0 locus reduction. And then you get a nice formula for the current algebra. So this is the key expression. And I've omitted all of the signs, which makes it look very nice. I was not able to find a collection of redefinitions that kills all of the signs. If you do, please let me know. Anyway, the point here is that the expressions to the left of the vertical lines, they are expressions, they are functions on the target space QP manifold. So instead of calculating Poisson brackets in the infinite dimensional space of currents, we have reduced this to a simple geometric manipulation, but on a graded supermanifold. And here, this QU comma V is, where is it? This expression with the V's and U's swapped around that gave us the generalized Lie derivative before. Whereas this is just the Poisson bracket on the QP target. Okay, and we get physically speaking, we also get what we expect. We get a term that corresponds to the we get a closed algebra of currents modulo this last term that involves derivatives of a delta function. That's the function of the eta over here. If you split the epsilons and etas out and insist on writing things in terms of Dirac deltas, you will eventually find that this corresponds to a derivative of the delta, which is the Springer term. So what can we do with this? For example, you can take your favorite brane and give geometric conditions for the vanishing of the 't-Hooft anomaly when you gauge a collection of currents. For example, if the currents correspond to functions on a DG Lagrangian submanifold, so one that is for which the Poisson bracket is 0 and which is closed under Q, you then get an anomaly-free current subalgebra. And an example of this is generalized complex structures in generalized geometry. Okay, so let's revisit our favorite example one more time to see what the currents look like. So we have 4 superfields, and then we do the reduction, then we end up with 2. And then we just write the current associated to a degree 1 function. If it's degree 1, it's linear in chi's and psi's. So it looks like a generalized vector. A section of tangent bundle over here and the cotangent bundle over here. And then we get this expression, where epsilon is either a function on the circle or a one form on the circle. And because we did psi is d of x, I've substituted that over here. So we get exactly the expressions that appeared here in the Alexeyev-Strobel algebra. This was no accident, of course. And indeed, if you evaluate this for epsilon a 0 form, you will pick out the one form component of the parenthesis because of how superintegrals work. And this will give you exactly the Alexeyev-Strobel one form currents. And, oh, okay, I seem to have sped through this quite a lot. That was really what I had to say. So I have some final remarks for you. So this works for any QP target, curly M, because we just have a construction of Poisson algebra. Well, assuming that you can make sense of the space of maps at that intermediate step, and that is a Poisson algebra, then the entire thing just works. Of course, if you take a very nasty QP manifold target such that the anchor map is maybe not of constant rank, you will not get a manifold, but in most relevant examples, they are very obviously infinite dimensional Poisson manifolds because they clearly arise from embeddings of branes into some target space supergravity background. For example, for the string, for this case, for example, we get the result we expect from string theory. Another thing that's nice about this point of view is that you can calculate the currents that generate spatial diffeomorphisms along the world volume. So if you want to discuss diffeomorphism in invariant brane dynamics, which is the correct thing to discuss, unless your branes have thickness or whatever, then you want the expression for these in general. And because the diffeomorphism T1 sigma, they have canonical generators, just vector fields on sigma, you can use a bit of Cartan's magic formula, etc., to just produce an expression for the spatial diffeo currents, which is very nice. Although the time diffeos are a mystery, although they do look like they should arise from some kind of QP structure, but the thing is, it's not quite known yet in general what generalized metrics look like from this graded symplectic viewpoint. So it's not clear how to deal with the Hamiltonian in this picture yet. Right. There's also a distinguished collection of currents such that they have a non-vanishing body. And which means if you set all of the ghosts and anti-ghosts to 0, these are the things that survive. And this collection of currents is the one that satisfies this condition, so that the degree of the associated function in target space is bounded above by the degree of the target space symplectic form minus 1. And these are precisely the same bundles that form the L infinity algebra of symmetries of the associated QP manifold. So from the symmetries of the QP manifold target, you get a collection of higher symmetries on the brane, a tensor hierarchy, we call them in, well, some physicists call them like that anyway. And I'll underline again that the QP manifolds for most interesting higher branes are known. For example, for the M5 brane, I wrote it a few years ago. And you can check that the phase space you get is exactly the correct result, including, in fact, the subsector corresponding to the self-dual gauge field on the M5 brane in the Hamiltonian formalism. And if you use the current algebra formula, you get, for example, that exceptional complex structures in E6 generalized geometry, which were put forward very recently, produce anomaly-free M5 brane currents. So physically, these complex structures arise if you have a supersymmetric background, for example, which is a situation you often want to have in M theory. So you've proven that similarly to strings, if you have supersymmetry, the supersymmetry manifests in terms of anomaly-free current subalgebras. And I will close with an open, so far open question, which is, what is the zero locus reduction geometrically, or if you want conceptually? I mean, algebraically, it's very nice, and there's nothing more to be said, I think. It's just a construction involving graded Poisson algebras, but there's something to be said geometrically, because this zero locus reduction, where is it? Over here. This is not symplectic reduction, okay? Because symplectic reduction does not change the degree of the symplectic form. So really, there's something to be said. Maybe it's a derived intersection, as some of you have suggested. I don't know. That's clearly the what I'll be thinking about in this direction, anyway. And that's it. So thanks for listening.
So thanks, Alex. Very nice talk. Yes. So, are there any questions? Sorry, which one? Sorry. Yeah, I looked. Okay. So who was the first one? So there is several questions. So sorry, I didn't see the order. So let me just let me start with Noriaki maybe.
Thank you. Can you hear me?
Yes.
Hi. Thank you very much for your nice talk. You mentioned the generalized geometry, exceptional geometry. So maybe your formulation should be related to duality, duality and U-duality. How can we see duality, the duality or U-duality in your current algebra formulation? Maybe it should be a canonical transformation on QP manifold.
Yes. So this is
yeah. Question is my question is that what is the relation with the duality transformations?
right. So it's a little bit complicated, but I do comment on this on the paper. But basically, the story is that the QP manifolds, where is it? Right, all of the QP manifolds mentioned in this table. So all of these capture generalized geometry or exceptional generalized geometry, at least in parts. So you get in degree p-1, you get the ring of functions corresponds to generalized vectors. You get a full duality multiplet there. And if you go down in degree, then you start getting incomplete multiplets, because one way to see that they're incomplete is that they should be complemented by brane, winding modes, etc. So it captures some of the duality covariance with regard to top form currents on the world volume. So for example, for strings, on the world space, for strings, top form means one form currents. They are these things. For 5 branes, you want to look at 5 form currents, and these are the things which assemble into E6 generalized vectors. And certainly for strings, we're currently working on how to see duality in terms of canonical transformations of these objects. And we expect the same is going to work for branes as well, although we haven't done branes yet.
Oh, thank you. Yeah, but maybe the I want to ask the relation with zero locus reduction with such a duality physics. Maybe zero locus relation should be also formulated as a kind of canonical transformation in QP manifold.
Yeah, I'd like to understand that better. I think it's certainly it's still a mystery, but so one idea. So Friedrich once pointed out to me that this degree shift, so from here with respect to here, is also what you expect if this zero locus reduction is some intersection of Lagrangian submanifolds in the BTVV formalism. But it's fair to say we haven't actually understood this point if that is the way to go.
Oh, okay. Thank you.
No problem.
Friedrich, you have to unmute yourself.
Oh, sorry. Yes, so thank you very much for the question. And yeah, let me now. Okay, so Eugene, do you still have a question or? Okay, then okay, let me unmute Donny. So Donny, please, Donald.
Yes, hi. So thank you very much for this very interesting talk. I have like a probably obvious question, but I kind of missed it, I think. So actually on this slide you're showing now, this Z, right? It looks kind of like a differential, right? It squares to 0 and it has the right degree. So you can like look at its cohomology. And if I understand correctly, these F tilde and G tilde, these are elements of the zero locus, right? So, I mean, elements of the cohomology actually, right? Because you say you have this equivalence.
Actually, no, because I don't demand that F and G, F1 and F2 are closed with respect to Z.
Okay, I see. Okay, so it's quite different from like a cohomological interpretation in sense of you, I don't know, have some kind of product which you induce on the cohomology.
Yes, indeed. I think there's some discussion of this point in this original reference, in fact. They relate the cohomology to sorry, what is it called? I think functions in the cohomology correspond to null directions for the Poisson bracket or something. They have a few more geometric remarks, but that's not a point that has come up for me personally.
I see, but would this way kind of give you a geometric interpretation of these things, or?
No, because I really want F1, I really want the F's and G's to not be necessarily closed. I mean, look at the bracket here. If G,
that's why I was asking.
Yeah, if G is closed, then the bracket is 0.
Yes.
So
I see. Okay.
Yeah.
Okay. Thank you.
No problem.
Very good. Thank you for the question. Yeah, are there any other questions? Yes, Eugene?
Yeah, I now have a different question. So from the one that got answered before. But can you say a bit more about your guiding principle? Like you said something about, oh, I have too many fields. So, and it seems like zero locus reduction gets you the answer you wanted, but why did you want that answer? Or, you know, what's the right number of superfields?
Well, let's look at the string case again, right? So this comes straight from the Navigator string. You define momenta for every position. You split the world sheet in time and space, right?
Mm-hmm.
So, and then you know that the things which see the QP structure in the form of generalized geometry in this case are these one-form currents. These are not just built off the momenta p mu, which is unconstrained. This thing is a derivative. So you want some kind of differential condition.
Why do you want this condition? I'm not following.
Well, I mean, the object here, the d sigma x mu, it's not a free variable. It's the derivative of something. And this is exactly what you get from the, sorry, what do I want to find? The zero locus reduction. So here you have 4 kinds of superfields. Fine, say, even if you look at the degree 0 bits of each, then you get too many things. You can form in degree 1 things which are linear in size and chi's. That's actually right over here. But then if you form this but replace the dx with a psi, then it's just, it doesn't have a derivative.
I see. So these are free variables you want it to actually, you don't want it to be an independent variable, you want it to be determined by another variable?
Exactly, and even more. So I chose to remove the M5 brane stuff from this version of the talk because it's too convoluted. But for the M5 brane in particular, the self-dual gauge field in the Hamiltonian formulation is a closed spatial freeform.
Mm-hmm.
So you want a differential condition that says d of that freeform is 0. And it actually comes out from the zero locus reduction. So that's the thing that really sold me that this is the correct thing.
I see. So your philosophy was physicists have written down some Poisson algebras.
Yeah.
And for various brane phase spaces. And you wanted to motivate this in terms of QP geometry. And the zero locus reduction is the ingredient that produced the Poisson algebras that you wanted.
Exactly. Even more, I mean, I can be even more practical than that. So if you try to calculate the Poisson bracket, something like this for a high dimensional brane, for the M5 brane, especially if the symplectic structure of the M5 is influenced by the introduction of 4-form and 7-form flux. I mean, it's a nightmare. I mean, sure, you can make students do it, but you'll run out of students. But this, this actually explains all of the empirical observations. And there's quite a few papers which I cite in mine that keep finding, hey, all of these current algebras close in terms of generalized geometry. Why is this happening?
Okay, thank you.
No problem.
Thank you for the question. Yeah, so we still have, okay, is there another question? We still have time. Okay, so it doesn't seem to be the case. So yeah, in that case, so let's thank Alex again for a very nice talk.
Oh, someone has a question.
Oh, or wait, no, I think that's clapping.
Oh,
it looks very similar, which is very confusing for this platform, but yeah. Okay, so I suggest to maybe to have a short break and then we continue at the full hour. So thanks again.